Okay, it's my pleasure to welcome you to the Borelli Award lecture. My name is Daryl Phelan, and I'm the past president, and I have the pleasure of serving as the awards chair for the past year. So we will have one of the awards today, the Borelli Award, and then we have another award session tomorrow where we'll distribute the A Award, the Young Investigator Awards, and the Journal Award. So the Borelli Award is our most prestigious honor given by the ASD. This award recognizes outstanding career accomplishment and is awarded annually to an investigator who has conducted exemplary research in any area of biomechanics. The Borelli Award has been given out annually since 1984, and we're fortunate that there's a number of Borelli Award winners in the audience, and I think I see a few future Borelli Award winners out there as well. So, joining the distinct class of Borelli Award winners this year is Dr. Ted Gross of the University of Washington for his work on studying how bone and bone cells respond to mechanical stimuli in normal and pathological situations. And I've invited Ron Zernicke, who served as his postdoctoral advisor at Calgary, to introduce Ted.
Thanks, Daryl. It's a personal pleasure and a professional privilege to be able to introduce Ted. As a Borelli Award winner this year, Dr. Clinton Rubin and I were very eager to nominate Ted for this award, primarily because Ted is not only an outstanding scientist, one who's made significant and creative contributions to science, but he's internationally known and recognized for the high quality of research that he's done. He's a superb mentor, and he has provided great service to the discipline. Just a little bit of a background, he did his undergraduate degree in engineering sciences at Trinity University in Texas, and then did a master's in sport biomechanics at Penn State, and then went to the State University of New York in Stony Brook to work with Clinton Rubin for his PhD in mechanical engineering. Actually, Ted and Clint met at a biomechanics conference, and I think it was a little over 30 years ago, something like this. And basically, in Clint's word, he said, after the session in which I gave my talk, a tall, inquisitive young man approached me to discuss the regulatory role of mechanical signals had in defining the musculoskeletal system. From that initial conversation at ASB, Ted basically went to work with Clint at Stony Brook, and it was a long and fruitful collaboration that resulted. When he completed his PhD at Stony Brook, I was very pleased that he was willing to come to Calgary to do a postdoctoral fellowship, and our collaborations have been very stimulating and unique over the last several years. Actually, one of the things that I must say is that when Ted came to Calgary, I didn't know how, I should say, unique or interesting it was to try and capture 60 or 70 pound turkeys in order to do some of the ulnar isolation studies in terms of bone adaptation. During his postdoctoral fellowship, following that, he basically accepted a faculty position in aerospace engineering and engineering mechanics in the Department of Orthopedic Surgery at the University of Cincinnati. From there, Ted was recruited to the University of Washington, where you can see, titles back shortly, where he's currently a professor and vice chair in the Department of Orthopedic Surgery and Sports Medicine, and he holds the Sigvard T. Hansen Jr. Endowed Chair in Orthopedic Traumatology. He's received many and numerous awards for his innovative research, and he has received continuing and very substantial peer-reviewed funding for his research for decades. Last year, he started his own spin-off company based on his discoveries, and that company is doing well. It's In Situ Therapeutic Solutions Incorporated. From the ASB standpoint, he served with distinction over these years. He was elected as Secretary-Treasurer, then elected President, and was recently awarded fellow status by the ASB. There's one quote that I can't resist in bringing out, and that was, after working with Ted for all these years, I'm frequently reminded of a quote by Albert Einstein. He basically said, to raise new questions, new possibilities, to regard old problems from a new angle requires creative imagination and marks real advances in science. Ted has always had the enviable ability to ask significant biologically relevant questions, and he has the ability to not only pose the questions, but also answer some of those questions. As you'll hear today, his ability to provide those new insights really into the complex world of bone mechanotransduction has taken along a very fascinating and enlightening path through bone, muscle, and nerve. Ted, please.
Thanks, Daryl, for the start of the introduction, Ron for the kind introduction, and then the challenge of a blank screen to start. That's pretty, it's like a dissertation test or something. So we're going to try this. There we go. All right. So I want to also thank the awards committee and the program committee and the society for such a humbling honor. As Ron mentioned, one of my first scientific meetings, actually my first national scientific meeting was in ASB. It was in 1985 in Ann Arbor. And the society's had, over those many years now, it turns out, has had a critical impact on numerous aspects of my scientific career. And that just makes this award even more of a special occasion for me. I wanted to first acknowledge our funding from NIH, and in particular NIANS, which has provided the majority of support for the work that I will describe today. And I also wanted to disclose my role as a co-founder of In Situ Therapeutic Solutions, as the last study that I'm going to describe resulted in the formation of this company. And as most of you are no doubt aware from attending Borelli lectures, or if you're now looking at your phones, looking it up on Wikipedia, Giovanni Borelli made very foundational contributions to our understanding of muscle and bone, in particular, and relevant to our interest in mechanobiology, the idea that muscles, by contracting about lever arms, are what enable us to have functional activity. And our own group's efforts at understanding the interaction between muscle and bone in terms of mechanotransduction are obviously a long descendant of this line of research. So I have divided the seminar into 3 sections. The first section is what I hope will be a mercifully, for all of us, brief background of me. A second section that's much longer that will talk about a series of studies working in the area of how muscle paralysis or muscle dysfunction causes a rapid adaptation in bone. And then a final section describing 2 recent studies that came out of almost those 15 years worth of research that took us in totally unexpected areas. So this is a photo from 1983, and I'm glad that most of the people are sitting further back, because there's a number of aspects of this that are quite embarrassing. The short shorts are really embarrassing. If you're not sure which one I am because there's hair, that's me. So this is in my senior season, and despite seeing the hair and that making me sad, I think about this picture sort of fondly, because this was a season where, for the first time, I began to experience and enjoy actually being a teammate. It was the first time where we were a very competitive team, and I was surrounded by players who were much better than I. And it gave me a chance to see what a group could do and how I could participate in a group. And just to reaffirm that, the 3 Trinity players that you can sort of partially see here are, in terms of the school's all-time scoring list, assist list, and rebound list, all 3 of them are still on that list. And the 4th Trinity player, you can see right here, is not. And I never was, for that matter. So, towards the end of my 4 years, I was on the phone with my parents. And my dad is a very directed person, and you'll tell by the digressions today that I tend to be not quite so directed. And he was impatient with my lack of progress towards finding a job, and suggested that he was going to do something about it, because he had just spent 2 weeks in the university library looking at various possibilities for me. And one of the possibilities, he said, was, I found out about this whole new field of sport biomechanics, and I think you should try to go to graduate school. And I was like a 13-year-old. I heard the sport part, and I got all excited. The biomechanics part, I didn't hear anything about. I ended up applying to Penn State, and over spring break, I called and did a phone interview and got accepted to the master's program. And a few months later, I loaded up everything I had in a little Honda Accord and drove 2 straight days from Central Texas to State College. And at 11:30 at night, I knocked on this sort of itinerant motel at the end of town. And Mario Lafortune, who has a very great French-Canadian accent that I won't try and do service to, opens the door in his shorts and says, welcome, here's a beer and here's the place on the floor. And it was actually, in retrospect, almost a perfect initiation to what being a graduate student was about. So at Penn State, I had the chance to learn from both Dick Nelson and Peter Cavanaugh, so that was sort of an exceptional experience. And I think in part of the value of that process for me was the extensive interaction we all had as graduate students. It was a very large lab, and there was a large number, predominantly PhD students, most of whom were, well, almost all of whom were much older, much wiser, much more experienced, and they were very embracing of the master's students like myself and Rodger down here. And I learned a lot about how the challenges of working in a group and also the benefits of working in a group, because many projects involve many of the students working together, usually on very tight deadlines. At the end of my time at Penn State, Peter Cavanaugh facilitated me to have the opportunity to go to an ASB in 1985 in Ann Arbor, as I mentioned. And one of the first sessions, that was when there was just 1 or 2 sessions, and there was a session on bone. And I went in knowing nothing about bone, and there was this guy standing up there with wild hair, and he was like all over the floor and the podium, and he was talking about turkeys and bone adaptation and Wolff's law, and it was intoxicating. And I really intoxicated was the idea that biology could be part of this. And my dad had a background in physiology, and so even though I never had explored that as a career option, I think that was maybe ingrained or something in me. And so the interesting part is that Ron told a little story of how I talked Clint into letting me be a graduate student. I actually have a little different remembrance. So 2 years later, I found him giving a talk at the ASB in Davis, and I waited until everybody was gone, and I basically badgered him until he took a chance on a PhD student who had really mediocre grades. And I just kept asking him, and he kept saying, well, why do you want to do a degree with me? Find somebody, go to so-and-so's lab or so-and-so's lab, they'd be way better. I'm like, no, I've decided. And I think in retrospect, because he hadn't had a PhD student before, his bar was really low, and that's what allowed him to take me in. So, as Ron mentioned, I had the opportunity to spend 2.5 years doing a postdoc with him at the University of Calgary. And he had just moved to Calgary from UCLA. And as I think back to that time, I think one of the exceptional parts about the experience was how much he encouraged me to do fringy biology things. As an example, we came up with this idea of measuring blood flow in bone, but neither of us had any experience in doing that. And so he encouraged me to go talk to Bob Ray, who at that time was doing blood flow in ligaments, and just sort of cajoled Bob into trying to help us figure out how to do the same thing in cortical bone. And I think that in a general sense, those of you who know both Ron and Clint realize that they're completely different personalities, but as mentors, they have a lot of the same similarities. I think that they were incredibly generous with their time. They were both able to show excitement about data that wasn't theirs. And they gave me a huge amount of room to pursue independent paths, not being very directed. And I thought that really was formative in my early start. And importantly, they gave me very different perspectives of how to succeed and build multidisciplinary, succeed with and build multidisciplinary groups. But probably more importantly, after all these years, they're still 2 of my closest friends. After finishing my training with Ron and Clint, as Ron mentioned, I went off to the University of Cincinnati. And by that time, I had some bit of a clue about Wolff's law, about what it was. It's the idea that promulgated in the 1850s by a German physician, Julius Wolff. It's the idea that the mechanical environment of the bone that's induced by functional activity causes changes in the morphology of the bone, and that there's some relationship, which is still undetermined. And in a more biologic sense, it has to do with how the cells within the bone, the osteocytes, which are the cells embedded in the bone that form a network of gap junction connections, sort of like a neural network, the osteoblasts that are on the surface of the bone that make bone, and the osteoclasts that are the macrophage cells that eat bone, how mechanical stimuli works with all those different cell types directly and indirectly to result in the end in changes in the shape of the bone. And in a non-biological sense, Roger Federer is a great example of that. And I also use this slide when I'm doing undergraduate lectures because it's a great example of the difference between causation and correlation. So the idea that Roger Federer has improved his hairstyle over years, that would be a correlation, not a causation. But the fact that he's been playing one-handed tennis for 30 years of his life has resulted in this massive hypertrophied right arm and this chicken wing left arm. And it's the idea that physical stimuli can be so anabolic for the skeleton, not just the muscle but the bone, which drives people in that field to try and understand those processes, to implement them, to countervene bone loss pathologies. And it remains an area of focus in our group. But what I wanted to talk about in terms of science today is sort of the other side of that. What happens when you have disuse? What happens when the lack of physical stimuli precipitates a process that results in reduced bone mass? And I wanted to start with a fairly short story. So this was about 15 years ago. We'd been at the University of Washington for a few years, and we were having trouble procuring turkeys. And it was turning into actually a disaster. And we met and we came up with a brilliant solution of not using turkeys anymore, but developing maybe some sort of rodent model. And at the time there were many different, and there still are many different rodent models of disuse, each with their own attributes and disadvantages. And we were considering some really complicated things, like we were going to go and do a surgery where we resected part of the fibula and we studied various adaptations of the fibula and things like that. And we had, right at that time, we had 2 undergraduate students, Blair Becker and Dave Sanford, who had actually worked in our lab as high school students and had gone off in their first year of university and came back. And they came and said they wanted to work again in the lab and that they'd like to try something innovative. And so we thought, well, hey, we're thinking about this model. Why don't we turn them loose on a literature search and let them try and come up with a new idea, because they're not quite as biased as we are about what you can and can't do. And so that was on a Friday. And so on a Monday, we're having a lab meeting. And before we can even start, Dave is like waving his hand, and he goes, so Blair and I were watching Nip Tuck this weekend. So for those of you who don't know what Nip Tuck is, it's like Miami Vice meets plastic surgery. It's pretty horrid TV. And he goes, we saw an episode where they were using Botox, and we wondered what would happen if you Botox the limb muscles of a mouse. And there's like complete silence in this room. And everybody is thinking, well, nobody knew how the experiment worked. We had no idea whether somebody had done that before and tried. But what we knew was that they had inadvertently hit this really small bullseye between those 2 things. So what did we know about muscle as a group at that time was very small. So in a general sense, mostly muscle was what we took away when we dissected after experiments so that we could get to the bones. The muscle went away. So we knew in a general sense that if you exercise, your muscles get bigger and your bones get bigger. And conversely, if you have either an acute situation or a chronic condition where you lose gravitational loading, you have a precipitation of loss of both muscle and bone. And the general consensus is that this relationship is very much guided by the mechanical environment of the 2 tissues. And part of that, I think, is because the conditions, experiments where you try and perturb one or the other are linked. So very rarely can you find a condition where you diminish muscle function and you don't also impair some aspect of the functional environment of the skeleton. So we did do a literature search. The internet existed by the time. And it turns out that a group in France had tried this. So they paralyzed the quadriceps of rats, and they had fairly macroscopic measures. They measured bone mineral content, and they measured trabecular fractal patterns with X-rays. And with those measures, they found about a 15 or 20% loss of bone, which is modest. And so we thought we could do better than that. We had this clever idea. We thought it was clever. We would paralyze the quadriceps and the calf muscles, and the mice would unweight their leg and limp around. So it would be a very non-invasive model of disuse. And so we implemented the study, and the first thing we noticed was that by 2 weeks, we couldn't tell the difference between the mice that we had paralyzed and the mice that we hadn't. So all gait dysfunction was gone by 2 weeks, but visually. Visually, it looks like the mice, instead of lifting their legs up, it looks like what they do is they ambulate just as somebody would right after a knee scope. So they partially weight their arm. And at that point, we had planned a 3-week experiment, and we almost just stopped the experiment and didn't do anything. And we went ahead and imaged. And so these are micro-CT images from a saline mouse at the distal femur, the proximal tibia, and the tibia midshaft, and likewise locations for a mouse that had been Botoxed. And this is at day 21. And you don't have to quantify, be too much into quantification to realize how much of the trabeculi is destroyed and how much of the inside of the bone, the endocortical surface, is expanded. And so that was pretty surprising given such a mild deficit. And in fact, that whole mixed interpretation of what we thought we were doing and what happened has driven this whole area of work for our group. A few years later, Steve Bain, who had joined our group as faculty, was sitting there, and we were discussing all these complicated experiments that we were going to do with our muscle paralysis model. And he said, why don't we do a simple experiment first? Because we don't even know when the bone loss occurs. And we're like, well, it occurs between 2 weeks and 3 weeks and blah, blah, blah. And so we, by that time, had an in vivo CT scanner so we could serially follow mice across time. And it turns out that the trabecular bone loss and the endocortical bone loss occur almost completely within the first 12 days. So this is CT imaging of the trabeculi from the proximal tibia of an individual mouse. And you can see by 5 days, 50% of the bone volume of tissue volume, is how much trabecular bone in the tissue area is lost by 5 days, and it's around 75% or more within 12 days. So this time course is much more rapid than what we had anticipated. And because of the rapidity of this and the type of the morphologic phenotype of the bone loss in the cortical bone and the cortical expansion, we anticipated that this loss was being caused by rapid osteoclastic activation, so osteoclasts of the cells in the knee bone. So this might be the only experiment in the whole talk where we actually anticipated an outcome, and it was actually the correct outcome. So we initiated a several-year collaboration with Paul Kosteniuk, who was at Amgen at the time, and Tony Alaprantis, who was at Harvard. And first we demonstrated histologically that osteoclasts, these are the osteoclasts right here, you can probably see them in the front row, they're elevated rapidly following muscle paralysis. And then we demonstrated in 2 separate studies. First, that we explored first whether osteoprotogerin, so that's a factor that competitively binds the rank receptor. Rank ligand binds the rank receptor as the primary means by which osteoclastogenesis is performed in the bone marrow. OPG competitively binds that receptor, so you diminish the number of osteoclasts. So it's been clinically approved and it's used to treat osteoporosis now. So in mice and in this model, it completely ameliorated bone loss. Then we used an inducible NFAT-C deletion mouse. So that NFAT-C is involved in transcriptional regulation of osteoclast function and generation. And the cool part of this mouse is that you can induce it, if you induce it right after birth, there are no osteoclasts, and it's a model of osteopetrosis, so that's the bone filled in solidly. But we waited until they were adults, so they had the same bone morphology, and then compared mice that had the deletion induced versus not, and what happened with paralysis, and it completely mitigated all of the bone loss. So at this point, we knew that it was a rank ligand-mediated osteoclastic process, which is a little different than what goes on in other rodent models. So rodents continue to grow, and usually in disuse with these type of models, changes in bone morphology and mass over time occur as a coupling of decreased osteoblast bone formation and increased osteoclastic bone resorption. And surprisingly, at least to me, these models are ordered from greatest deprivation of gravitational loading. So if you have Hyman suspension, you have no gravitational loading, to least deprivation of gravitational loading, gait loading. The sciatic neurectomy, the gait and the mass are obviously different, but the amount of ground reaction forces are nearly the same. And then the various changes in trabecular bone, cortical thickness, which is a marker of cortical bone loss in this case, and muscle mass. And you can see that we have a fairly modest gait defect yet, or at least at that time we claimed we did. Yet we have this profound amount of bone loss that occurs way faster than these other models. So finally, around that time, actually Sarah Mast, who was a PhD student with Ron, had published some data suggesting that, or indicating that when you Botox mice, they have about a 20 to 30% reduction in ground reaction forces. And we wanted to build on that observation and couple it with another model that allowed us to begin to separate out the gait-involved or gait dysfunction causes of this pathway with the neuromuscular dysfunction causes of this pathway. And so we implemented a model of peripheral nerve injury with PNI. So Steve Bain brought that with him to the University of Washington. So this is a model that's used in the pain world, and it involves surgically identifying the sciatic nerve, putting a little silastic tube that fits loosely over the nerve, and then you suture up. So the nerve gets irritated big time by this tube, and the limb becomes hypersensitive to touch. And we had known from a previous study that there was bone loss involved in this model. So this is an idea of coupling Botox and nerve injury we went back to sort of our Gait roots and got Gait kinetics and Gait kinematics and used those to develop a quantification of the normal strains on the mouse tibia during Gait and how that varied with these two conditions of varying musculoskeletal and neuronal involvement, and then basically look for correlations. And so I just want to point out Phil Huber in the corner. He is primarily works with our imaging stuff, but he's also a mouse whisperer. So it turns out, unlike the first talk of the meeting, where shrimp are very attracted to 3D printed cylinders, mice are not. Turns out what they love are little pieces of gummy bear. So Phil found that out, and that's how you get them to walk over and over until you get the same speed. So this is free walking. So first on the left, both of the mice on day 0. And you can see, since I grew up in Texas, it's sort of a giddy up. It sort of moved down the runway. So now we're going to look at the Botox mouse on day 0 and day 5. So a couple things are interesting to me. One is that the orientation of the gait, the position of the body position is changed. So the spine is more arched, and it is sort of hopping along over as it moves on the right limb. Nerve injury also has a change in body position, but it's almost the exact opposite. It's sort of slinking along. That's a technical gait term that I'm using. And still loading. So in general, what happens, it turns out for the nerve injury, there's no change in muscle volume. There's about half the amount of trabecular bone loss as you see in Botox. There is about a 20% decrease, 20 to 30% decrease in peak normal strains for the Botox. There's very modest changes, like 5% change of peak normal strains for the nerve injury. And so when you put all this data together and regress the change in normal strain across all these time points versus the trabecular BVTV is statistically significant and predicts very little of the spread of the data. On the other hand, just regressing the change in muscle volume, which in this case is a surrogate for how severe the neuromuscular injury was, predicts substantially more of the spread of the data. And so knowing nothing about the mechanical environment and how that's changed is a pretty strong predictor. And that's the idea. I think at this point, we're not dismissing the fact that mechanical strain has something to do with the loss of bone in this model, but it's pushed us into other areas of thinking about how this loss could occur. What is the signaling path that leads to such rapid resorption? So we, at this point, decided we sort of shift gears. And what we wanted to do is find out where the osteoclasts were showing up, because we thought that might give us a clue about the type of pathways, because there are different, even within the same bone, there are different microenvironments. For example, near the metastasis is much more innervated than in the diaphysis. And Brandon Ost, as part of his dissertation, had worked out a means of realigning cortical bone images over time in this model. And he and Phil had worked together to apply that technique to allow us to align trabecular bone images taken from the same mouse over time. So the advantage of this, the reason it worked is that in this model, phenotypically, there's no change on the periosteum of the bone. So that's a consistent landmark volume that you can realign everything to over time. All the changes are internal. The advantage is it allows us to objectively look to see where resorption is occurring, when all the other techniques for alignment require some subjective best fitting. And you can see, even when you align on the top, when you just put a mouse in and scan twice, even if you have a little rig like we do, it's never going to be, you're talking microns difference. Things are not aligned, whereas with all the green in the lower right, you can see that it's a fairly accurate means of doing this. And then Brandon was able to apply that in an in vivo experiment, where he's looking at the proximal metastasis of the tibia. And as I mentioned, mice grow, and so their growth plates are not fused. So there's right below the growth plate, there's actually active remodeling. So there's osteoblast and osteoclast activity. And in this three-dimensional matrix, any cube where there's a net resorption versus day 1 is in red. And you can see that in day 2, in naive mice, there's this little resorptive area right at the top and centered in the metastasis. And in Botox mice, that's the same. Day 3, no change in the naive, and yet here on day 3, in the Botox mice, you see where the resorption is occurring. So it's not occurring everywhere at once. It's starting in one area and sort of filtering through the tissue quickly. So this suggested a couple possibilities, and I mentioned nerves, and also suggested the potential, because it's heavily vascularized there, the potential for inflammatory cytokines. And we turned to doing some RT-PCR gene screening in bone marrow following muscle paralysis. And one of the genes that popped up was TNF-alpha. So TNF-alpha is a primary mediator of inflammation, not just in bone, but throughout the body. And it had this really rapid peak right around day 3, which is the time point where we're starting to see osteoclastic, at a tissue level, osteoclastic resorption. And so Brandon came up with the help of Leah Wharton in our group with this experiment where we paralyzed mice, and at whatever time point after paralysis, we took their bone marrow out and we did primary osteoclast culture. Because we had this idea that, of course, if we take bone marrow from day 3 versus day 1 or naive mice, we're going to get many more osteoclasts in culture. So that didn't work. There was no change. But while he was doing this, Brandon noticed there was a huge difference in the number of giant osteoclasts. Giant osteoclasts are phenotypically associated with bone loss pathologies that have inflammation, so Paget's disease or rheumatoid arthritis. And when they are active, they consume disproportionately vast amounts of bone. So they step up to the bone buffet and clear it out. So you can conceive of, in a situation where we have relatively less trabeculi in a mouse tibia than you would in a human, how a few of these giant osteoclasts could basically graze through there in a few days, and it would be all gone. So here at this point, we thought we were going to do the concluding study of this whole series of studies, because now we've seen TNF-alpha, we've seen this inflammatory cascade, we have giant osteoclasts. We're going to paralyze mice that have defects in various aspects of the TNF-alpha signaling cascade and show that mitigates bone loss. And as you might expect from the way of my tone, it did not. So this is a TNF-alpha knockout, this is a toll-like receptor knockout, and this is a T-cell knockout. And there was no change. There was no change in how fast the bone was lost. There was no change in the magnitude of the loss. And so at that point, we stepped back again and began to think, how could we get, in a sense, it makes some sense, because most inflammatory pathways, if you talk to somebody who works in that area, they take much longer than a few days. The inflammatory cascade and the buildup is a very slow buildup. And what we were looking for was something obviously much faster. So one thing that happens with trauma and neuromuscular trauma in particular is the initiation of something called neurogenic inflammation. So neurogenic inflammation consists of an injury and an antidromic afferent result from the sensory neurons where it precipitates a dump of neuropeptides into whatever environment. And the whole idea of this is it's almost like a shock response to rapidly induce a positive feedback system, a local positive feedback system for an injury response. And so one example is that the neuropeptides are dumped, mast cells are there, mast cells produce things that induce greater amounts of neuropeptides, and then mast cells do other things. So our idea was that potentially we were looking at part of the pathway, but there's another part that was actually controlling it. And Leah Wharton, who at the time was a postdoc and now a faculty member, brought a great deal of expertise with molecular biology to our group. And she did the hard work of actually doing Western blots on bone marrow. And so this is a Western blot for substance P, one of the neuropeptides involved in neurogenic inflammation. Substance P and CGRP are the sort of the hallmark neuropeptides. This is substance P in the brain, left and right limbs, so from the bone marrow. This is naive mouse, and day 1, 3, and 14. You can see the upregulation, the bone in the brain, lack of substance P expression in the naive mice, and upregulation day 1 and 3. And because Western blots are notoriously finicky and non-quantifiable usually, we've confirmed those results with ELISA. One of the interesting aspects was that CGRP was not altered at all at those time points. So immediately we launch off on our finding it, going through the Jackson library and finding a mouse that has a deficiency in substance P. It's a TAC1 null mouse, so it has a defect that doesn't not allow it to produce substance P throughout the whole body. And what we found was that it modestly altered bone mass. So this is wild-type mice at day 0 and 4. The red's the trabeculi and the proximal tibia. You can see some of these trabeculi are already perforated. Not much going on with the TAC null mouse. And so what happens is that it delays the onset of bone resorption in this model. And there's about a 15% decrease at day 12. So there's a number of explanations. One is we're totally off base, which is not encouraging. Two, another possibility is the TAC1 mice has developed and is known to have developed other means of doing neurogenic inflammation. So there are compensatory pathways in this mouth because it's a congenital defect. There are compensatory pathways that allow it to do neurogenic inflammation. And the third is probably this is happening before any of the time points we've explored to this date, and so we don't know. Their CGRP could be massively upregulated. We just picked the wrong time point. One characteristic of these data is they go up and down really quickly, and so we're trying to use alternate strategies to try and ferret out the timing of this. And at this point, we thought rather than chasing after more mice, we'd chase a little bit part of that other pathway of the mast cell. And Edith Gardner, who joined our group a few years ago as a faculty member, has a deep expertise in neuropeptide signaling, neuropeptide Y, and bone cell function. And it turns out she's a mast cell man. She's really interested in mast cells. And so we were talking about it, and we decided to do the same type of experiment, except for this time the RT-PCR panel was focused on mast cells. And you can see in red are all the increased genes, and all of these are genes related to mast cells. But there's this predominant elevation of mast cell genes related to mast cell activation and mast cell function that occur and then are completely back down to zero by day 14 when all of the bone resorption model is complete. So what kind of model does this give us? So right now, and this is highly speculative, we're working on the idea that when you inhibit function, neuromuscular function, you send antidromic signals into the marrow space from the muscle through the spinal column. That results in substance P elevation of CGRP or some other neuropeptide that is involved in this process. Those neuropeptides act on mast cells. Mast cells via histamine release are known to be associated with the formation of giant osteoclasts and also the release of additional substance P. So it creates this really rapid positive feedback loop. And so we're working on that. I think in the perspective, the broader perspective, one of the interesting things is there's evidence in the literature that this is not just a muscle paralysis phenomenon. So this group was doing space biology out of Japan 15 years ago almost, and they did this unbelievably difficult but fascinating experiment where they instrumented the spines of rats and then flew them in a parabolic flight, and they found afferent signaling changes in the spine during the parabolic flight. So within 15 seconds of weightlessness, there's already signals coming back to the spine saying something's wrong. And they were able to confirm that these same pathways are there for Heinlein suspension. So, just speculating, I think that the possibilities are that this is a very common, a conserved mechanism, not just associated with paralysis-induced bone loss, but other types of gravity-induced, in this case, microgravity-induced bone loss. And might be one potential explanation for, just like in our studies, we have had challenges in terms of inhibiting this loss. The exercise has not been hugely successful in inhibiting bone loss in space. So I have no idea where I am with time, but I have 10 minutes or so you can set your clock by that. So the final bit is about two studies that have taken us into totally different areas. And so I've mentioned Steve Bain a couple times. This is Steve right here. His other job and complete passion is as a university volleyball coach at Northwestern University, the NAI school in Kirkland, which is right next to Seattle. And our daughter had started on the path of progressing through club volleyball and becoming a setter. So she's had a chance to be actually coached a little bit by him. And he's full of pithy coaching sayings. And one of them, I actually had to ask our daughter Sydney what it meant. Hitters go where the set takes them. And the idea is that the hitters make the setter look good by not trying to do too much, just accepting where the ball is being set and making the appropriate play. The ball's tight to the net, you don't try and stuff it through 6 people, you just make a simple play. And I think it's a little belabored, but I think the same idea underlies some of these studies that I'm going to talk about in a few seconds, where just being open to results that were non-intuitive or surprising has led us into totally different areas. We just, instead of being too stubborn and resistant, we just sort of moved on to something else. So I've described our muscle paralysis model. Sundar Srinivasan, who is also faculty in our group, was instrumental in the development of a mouse cantilever bending loader. So the obvious experiment is why don't we do all types of loading studies. We've generated ideas of how to make loading very osteogenic with very low magnitude loading. Why don't we use the loader and inhibit the bone loss? And so we tried the experiment. And we actually tried it 3 times. And so we use CT imaging over the course of this 3-week experiment. And this is a group of mice that were Botox but not loaded. You can see about a 30% change in muscle volume. Muscle mass changes about 50%. Saline plus loading, there's no change in muscle volume. And as you might expect, loading the tibia doesn't do anything for the muscle paralysis, induced muscle loss. Sadly for us, each of the 3 times, it didn't do anything in terms of the bone resorption. So the bigger the endocortical volume, the more the bone is resorbed from the inside. This is a consistent between 8 and 10% change at this time point. And it's identical for Botox and no load, and Botox plus load. So we were basically giving up on the study, and unbeknownst to us, Dwayne Threep, who is a research scientist in our group, had gone ahead and processed the tissues. We'd actually just weren't even paying attention anymore to the study and doing something else. And as he does almost all the histology in our group, and he comes running in and he says, I think you need to look at these slides. And he shows me a slide of one of the mice that we had loaded after we had Botoxed it, and it had a humongous amount of bone formation, more bone formation than we've ever seen in the model. And so what we did was we came up with a simpler experiment. We were going to load the mouse with a very modest loading waveform that, without anything else, would do a small but significant increase in bone formation, and then see what happened when we did the same loading regimen with a Botox mouse. And it turns out when you Botox the calf muscle, you get a lot more bone formation. Right? So the green is calcium label that chelates with the osteoid that the osteoblasts secrete, and you can see that when you just have this loading waveform, generates a little bit of periosteal bone formation or osteoblast activity, and it's a vast amount more for Botox plus loading. So the next, we actually quantify that. And it's depending on the loading waveform you use, it's about a doubling the response. So the next experiment, we thought we would move the paralyzed muscle around, and we would show that it's a very local effect, that if you paralyze some other muscle in the animal, you would abolish the effect. And that's not true. So these are mice that had saline injections and load, left calf paralyzed, right triceps in the forelimb, and right calf. And you can see that no matter where we moved it, it had the same response. So right around this time, I had gone to a seminar at the American Society of Biomechanics Research, and Eric Olson had given a talk about microRNAs, which were, for those who don't know, those are small non-coding nucleotides, 20 to 25. And they were only identified in, it sounds weird to say, the late 1900s. And only around 2002 or 3 did people realize how potent these were in the body. And not only potent within a cell, but they have the potential to act on distant cells. So there are many companies now focused totally on exploring this as treatment for cardiovascular disease, ALS, various diseases. And Eric, I went back and read this great paper that he had talked about. And they pretty definitive, as you might expect from publishing science, they pretty definitively demonstrated that this specific mirror, 206, was critical for neuromuscular regeneration following both neurectomy and the onset of ALS. So it's when neuromuscular function ceases or is impaired and the nerves try and resprout. Mirror 206 is really essential for that process. We thought, why don't we see if that's happening with Botox? And Ron Kwan had joined our group at that time as a postdoc. He's since gone on to start his own group doing zebrafish fin regeneration work. But he brought screening techniques that we didn't have before. And in screening, we screen for a bunch of mirrors, and we screen for various growth factors and things like that might be associated with enhanced anabolism. And mirror 2206 is booming. And RT-PCR confirmed it, and the upregulation of this in the muscle is one thing, but how could it get to a distant site? Well, the way mirrors get to distant sites in one way is via packaging of exosomes, which are secreted and float around. And so this is data from demonstrating that exosomes in the serum from mice that have been Botoxed have elevated levels of mirror 206. So I think this is in its infancy. I don't know that this is really skeletal, but the idea, I think, is really appealing. That on one hand, we know that muscle paralysis has a really catabolic effect on the skeleton, but at the same time, it has the potential, if we understand the pathways by which it's acting, to actually have an enhanced anabolic effect. It could be if you could uncouple those relationships, you could target and use this prophylactically to augment bone formation. And one of the interesting aspects is it's not potent enough on its own to initiate osteoblastic activity, without the loading. The loading is essential. Loading creates the osteoblast to function, and when the osteoblasts are turned on by the loading, in the presence of exosomes or whatever, if we're wrong, some other factor, the factor, in this case, miR-206, which acts by, miRs tend to be inhibitors. So it inhibits HDAC4, which is a histone deacetylase. That inhibits, among other things, RUNX2, which is a key transcription factor in osteoblasts. So it's a biological process that's very conserved across species and cell types, where by removing an inhibition, you can rapidly start something. So it's a very appealing, I think, a very appealing biological type of pathway. So the last bit is talking about fracture biology and heterotopic ossification. So this is actually data from a study that we started with Steve Bain before he came to UW. And we were using the Tom Einhorn fracture model, and where you pin through the femur and you break it and look for healing. And it's a very well-established model. And our idea was that we knew from the muscle paralysis studies that we partially reduce weight bearing in these mice, and or in this case rats. And one of the weird things about the rat healing, I mean, if you were to fracture a bone like that, you wouldn't be walking around on it a few hours later while they did. And our idea was, if we impaired some of the locomotion, that would give the bone a better chance to heal, and we'd have enhanced healing. And so, as the theme has been, that's not what happened. If you look at the bottom, clinically you classify this as hypotrophic non-union. So lack of healing of the defect, the fracture itself, and a lack of periosteal callus. And since we were at that time interested in the mechanical component of this, we wanted to move to a model where we could quantify where the changes in the mechanical environment. And Jitendra Prasad was working with us at that time as a postdoc, and he did all the hard work in generating strain estimates near cortical defects in the mouse tibia during Gait. And so the idea we had was that by moving the defect to different sites, the healing defect would be exposed to different types of strain. So compression, tension, and neutral axis. Oddly, the greatest healing occurred at the neutral axis, so we have no idea about that. This slide. So here are serial CT images from a mouse that had a medial defect and had a saline injection, and a medial defect and a Botox injection. So we went back to this Botox idea. And I'm going to try and do this without fouling this up. So you can see the prolific fracture callus and then the healing defect. And I'm going to try and stop it in the healing defect. Do that. So that's like really pronounced healing defect. And then this is what happens when you paralyze the calf muscle. So there's no fracture callus, but the totally bizarre thing is that it's still healed. So if you look at the defect, it still has the same healing in the defect. So Steve and I saw these images at the same time, and we both thought that, there's a biological reason for periosteal callus when you fracture the bone. There's not really a biological reason. There's no structural reason for the periosteal callus to be there when you have a defect. It's not a critical defect. And we thought that maybe this actually could be used in a different sense, to control bone growing where it shouldn't. And that is what heterotopic ossification is. So heterotopic ossification is formation of bone, usually in muscle. It's a sequelae of various types of trauma, usually superimposed on some sort of neuromuscular injury or brain injury. And there are no good treatments for it. Basically, the treatment is, if it gets really painful and it fuses your joint, we'll go in and hack it out. And in that case, often it just grows back because the same cellular environment is there that created it in the first place. And there's no way of predicting who's going to get it or who's not at the time of the trauma. And so we used a mouse model of BMP-induced HO, and the red is the HO, the muscle, the tibia, and you get this lumping bit of bone that forms. You just inject BMP in matrix gel, and several weeks later, there's a huge amount of bone. So the BMP2 drives the cells in that area to become osteoblasts and make bone. And if you do the same model, but you inject Botox, you greatly diminish the amount of HO that's formed. Depending on when you look, between 50 and 80% of the HO is mitigated. And so we designed an experiment where we would show that, to facilitate translation, that you don't have to be right on top of the HO, you just have to paralyze the muscle. And so we did that in this model where we compared a targeted, or called a remote injection, and the BMPs are injected up here by the targeted Botox. and the remote is 4 millimeters away. And so in terms of the muscle paralysis, it's the same. So we paralyze, relatively it's a small muscle, we paralyze all of the calf, and so you get the same amount of muscle loss. Unfortunately, that's not what happened with the bone. So we completely abrogated the response by moving just 4 millimeters away. And what this means, at least our interpretation of this, is that it's not the muscle paralysis that's inhibiting, it's the distribution of this neuromuscular inhibitor. And that makes a little bit of sense with what's known about HO, because one of the primary pathways by which it forms is dysregulation of BMPs in the neuromuscular junction. So the idea that resulted in the transfer of technology was that you would have to come up with a device to distribute this for the various clinical indications. Brandon and I spent hours, because we're both Games of Thrones fans, we spent hours coming up with what we thought was going to be the name of the company. And for those of you, this is our first tech transfer process. For those of you who have gone through that process, you probably surmised that lasted about 4 minutes. Nobody thought it was humorous at the least. We were very sad. So I'm going to close up with just a few slides and come back to Borelli. And I hope I've given you a flavor for how our studies have followed on this seminal observation linking muscle and bone from a biological perspective. And also I hope I've, without belaboring too much, convinced you that nerves and neuromuscular health plays a critical mediating role between these two tissues. I also want to emphasize one more time that none of this work would have happened without the intense collaboration with incredible people that I've worked with and who happen to be scientists. And our efforts to be selfless about our ideas with each other, to be constructive about criticism, and try to do it with a sense of humor. It doesn't always work. It's harder than it seems sometimes. But none of this work would have happened. And really, all the people I mentioned were actually involved in multiple projects, not just the one I mentioned. And I wanted to note, thank Peter Stern and Rick Matson at Cincinnati, Washington, who recruited us. And uniquely for clinical departments, they had a long-term vision that gave us room to explore aspects of bone biology whose potential for translation, I think, is pretty vague, even to us. And but then in the end, sometimes you actually get to something that is translatable. So I really appreciate their vision that allowed that to happen. And I wanted to thank also my wife, Allison, and our daughter, Sydney. Neither could be here today for different reasons. Our daughter, probably way happier, is canoeing and kayaking in Puget Sound. And my wife, who's probably now tired of the newest member of our family, is the sole caregiver right now for a 10-week-old yellow lab. And I really think that, honestly, every day that I get to hang out with them, they're nice enough to let me hang out with them. It's a great day. And so I couldn't have done anything like this without them. So thanks for your attention. I'm sorry it took so long. I'm glad to answer any questions also.
Thank you, Ted, for a fabulous talk and putting up with the technical difficulties. And for that, you are awarded the Borelli Award. Not for putting up with the difficulties, for the talk is the award. Right? So on behalf of the society, it's my pleasure to give you this award.
Thanks.
Hi, Carol. Welcome from BTXA. That was very calm, despite all the technical difficulties. I saw that it seems that a lot of your results have stemmed from the tibia and the long bones, and I was wondering if you could speak to how this might apply to other types of bones or bones that form from membranous ossification.
So we haven't done that work, but other groups have. So one of the things I forgot to mention, one of the interesting aspects, so when we started this, there really wasn't much study of muscle paralysis induced bone loss. And it turns out it's incredibly conserved. So including spine and jaw and cranial across chickens and fish and mice and rats and pigs and sheep, and there's even been reports of humans. So they've actually gone back and looked at people that have been receiving plastic surgery type Botox, and it seems to be a very conserved pathway. I think the reality is for the different animals, the different locations, the magnitude is going to be different. And honestly, one of the reasons we devastate the bone in the proximal tibia of C57 mice is that there's not much bone there. When you do it, you still can see a huge loss in other mice, but that same percentage loss is just, it's not all gone because they have more to start with.
Great talk.
I usually judge talks by how many questions and how many ideas I get. We've got about 10,000 ideas, so I'm not sure if the poster session can wait that long. Maybe you can ask one. Nobody else has a question to ask.
Please, somebody help me.
So the one thing that I was really wondering conceptually is, Botox spreads, but you're talking about these effects when you injected the remote sites, and I'm just wondering, have you ever looked at the systemic effect on muscles when you went into specific sites? Because in our hands it seems to affect all kinds of muscles really far away.
Yeah. So yeah, I didn't have time to talk about that. So there are systemic it's more bilateral effects than systemic effects in our hands. And interestingly, with these different models, there's different levels of bilateral effects. And so Steve Bain in our group has actually been super interested in the whole idea of how the brain processes symmetry in the skeleton and musculoskeletal symmetry. And this isn't exactly an answer to your question, but for instance, the Botox we find in our hands, has less of a bilateral effect. So you might lose 80% of the bone and 50% of the muscle, and it might be 5% of the muscle and 10% of the bone on the contralateral side. The nerve injury, which is much less of a robust catabolic challenge, you lose 40% of the bone volume on the ipsilateral side, and on the contralateral side, it's almost the same. So I think that there's some really interesting aspects of this that we have no idea about. That there has to be some sort of higher level processing of information that we don't understand. And we've tried some experiments where we move things around, but obviously there are other factors that overlay that. Oh, come on.
I'll ask a quick one before anybody else says. The other thing I was really interested in is, that you're talking about the neurogenic inflammation and the effects it has. Very, very impressive. And since you're talking, I'm really interested in obesity, metabolic disease, and the systemic inflammation there. Do you know anything about that? Has anybody ever looked at that in terms of bone adaptation, the systemic inflammation of obesity?
Yeah, so we haven't. We are doing some of these studies associated with how these processes might change with aging. And so superposition of adrenergic signaling changes in the body as you age. But the field of fat metabolism and adipocyte function is a booming field of bone. It's probably the hottest area right now. And the whole idea in general, Cliff Notes version of it, if they do Cliff Notes, Wikipedia version, is that cells that commit to being adipocytes can't become osteoblasts. They have a common precursor. And so you're basically, if you have a systemic situation, an inflammatory system, you're going to tilt towards osteoblast or adipocytic differentiation. And those adipocytes are known to feed inflammatory cytokines. So again, a very general thing, but it's a really cool area.
I'll say it. Is that okay?
Thank you.
You're postulated. So if you look at all, I know they use like bone stimulators on bones. If you look at all like electrical current effect on bone, both positive and negative.
Yeah. So we haven't directly electrically stimulated bone. We actually, the first experimental funding we got for the muscle paralysis stuff was from the Christopher Reeve Foundation, and we had the obvious idea that we would just use ECM and that would solve the problem. And it turned out it was no more effective than loading bone directly. And I think it's an odd. I think what's happened is a lot of the interventions we've tried are just too slow and too late. These signals are happening so quickly that the signals for osteoclastic changes are within a few days or a few hours, and then they're effective within a few days. And a lot of the loading regimens you start a day or two later. And I think, like a lot of the interventions for spinal cord injury patients, they have all kinds of health issues, all kinds of psychological issues. The physical therapy interventions are way down the line. And honestly, I think by then the bone has already decided what it's going to decide. So most of the interventions there are good reasons to do them, but in terms of bone health, are probably pretty ineffective.
What if it's not like a spinal cord injury, but just a healthy person who would get an injury like a stress fracture?
Right.
Have you looked at anything like that?
We haven't. I know Clint has done some work where they have a vibration device, a low magnitude vibration device, and I know clinically, I don't know whether it's actually off-label or whatever, but I know it's been used with some athletes who have had stress fractures to promote healing, but it's sort of anecdotal, and I don't know whether it's actually helping or not.
from the University of Oregon. Thank you for the great talk. I'm curious if any of your research looks at aging and how some of the things you have found could potentially be translated into that realm of research.
Yeah, so we haven't, aging hasn't been like a primary focus, but over the years it's sort of come in and out of different studies. So Srinivasan, who I mentioned, has done a lot of loading studies with aged mice, and the idea that there are certain aspects of the mechanotransduction pathway that might be targeted to enhance. So one thing that happens in old folks is that the same exercise that was anabolic when you were younger is now no longer anabolic. And the potential explanations are that the osteoblasts can't do it anymore, or they can do it, but they're just not getting the same signals. And so in that area, he's actually identified interesting aspects of the calcium signaling regulation that serve via modulating that by cyclosporin that actually seem to restore some of that. And I also mentioned Edith Gardner. She's interested in adrenergic signaling. So one of the things, adrenergic signaling it's altered with age, and it has a repressive effect on bone cells, in addition to many other cardiovascular cells and things like that. And so it turns out if you inhibit that repression in an old animal, you can restore their loading ability back to normal. The mouse studies we've done with paralysis in aged mice have been a little bit of a disaster, because basically it's the same severe response, and it just eats a hole in the bone, so we stopped for safety reasons, stopped it.